Hi, my name is Koraju and I'm going to present Lab 5 Faraday's Law. Starting from introduction, so the purpose of this lab is to do experiment and simulation to observe and visualize the time-varying magnetic field and the corresponding induced current according to Faraday's law. So equations or the physical principles behind this lab. First of all, Faraday's law, I is equal to EMF over R, and here's another equation telling the d flux over dt. And also we need an equation to calculate the magnetic force on loop. The sine theta here can also be calculated as the equation I listed. For the last part of the coding part, we need to apply Newton's second law. So this is a revision of Newton's second law. So for the lab itself, we need to prepare a magnet and an aluminum coil. So basically, we just drop the magnet into the coil tube and record the seconds it requires to travel through it. And here are two screenshots from my lab video representing the moment of the magnet entering the tube and exiting the cube. And I repeat this experiment for 5 times, getting an average result of 0.62 seconds. Then it is the simulation part, which requires coding. So first I listed all my initial values from my lab. So the length of the coil tube is 0.29 meters. The width of the foil is 0.008 and the inner radius is about 0.02 meters. Then I measure the mass of the magnet and I also get the mu magnet from lab 3. The second step is to get the dipole function, which also can be copied from lab 3. And then we need a new function calculating d flux over dt. And I've already mentioned the equation we use from the introduction part, so we just plug in those equations and get the function. And third step, first listed out the gravitational force to be later used. And I is equal to EMF over R, but EMF is equal to negative d flux over dt. So that is how I get the current here. Applying the equation to calculate force on loop, we can get the stuff I listed here. For the very last part, we just apply Newton's second law, which is Vf is equal to Vi plus A times dt, and Yf is equal to Yi plus V times dt. So we can get the bar velocity and the bar position here. And F net is equal to magnetic force plus the gravitational force. This is the result I get. Here is a little video representing the visual presentation. So as you can see, there are two rings, one red and one blue, representing the induced current above the magnet and below the magnet. And the gray tube here represents the coil tube. And I'm getting a velocity versus time diagram as presented. It is said that time in the tube is about 1.11 seconds in the simulation. So for interpreting the simulation, the red ring represents the clockwise current and the blue ring represents the counterclockwise current. That is because when the magnet is falling down the tube, the magnetic flux is downward. So according to the right hand rule, it is experiencing a clockwise current, and that is for the red ring. And since the induced dipole is opposed to that magnetic field, so it actually has a opposite direction of the current. And if we flip the magnet around, it would, like, the induced current would change directions. So I think the red and blue ring would flip. So which means the induced dipole is now in clockwise direction. So for the real world system, I'm getting a result of 0.62 seconds for the magnet to travel through the tube, and the computational model is 1.11 seconds. There is a relatively large difference between them. I guess that is because the magnetic dipole moment I get from lab 3 is relatively large, which is 3.14. I've tried to lower it down a little bit, and it will actually decrease the difference between my real world system and the computational model. And the slope of the plot is 0 for the velocity versus the time plot, indicating that the net force acting on the bar magnet is equal to 0 during the time it travels in the tube. Some further discussions. So what if the resistivity of the conductor were reduced as close as possible to 0? I'm assuming that the induced current will be larger since the resistance is smaller, and the magnetic force upward will be larger as well, so therefore it takes longer time for the magnet to travel through the tube. And also, what if holes or slots were cut into tubes? What would this affect the currents in the model? So I'm assuming the induced current would be smaller, and the magnetic force upward would decrease, so therefore it takes shorter time in the magnet to travel through the tube. Simple conclusion. So this lab helps us to visualize the concept of Faraday's law by both experiment and simulation program. And it also helps us to review concepts like Newton's second law, induced current direction, Beal-Savart law, and definition of current, etc. So that's it. Thank you.